Okay, so we're going to look at probably the most prominent way of adding vectors, and that's using the vector components. So this is the algebraic method of vector addition. And basically start off, we can understand that a vector is basically any quantity that has a scalar or a magnitude and a direction. And this, let's say this is vector A. All vectors can be broken down as a sum of its two-dimensional or three-dimensional components. Now, for the time being, we're only looking at two-dimensional vectors, so vectors that exist on the x and y plane, right? And if we have a two-dimensional vector, such as this, right? If we're looking at this in R2 space, it's going to have a specific x value and a specific y value. So every vector in 2 or 3 dimensions can be written as a sum of its components. And this is what I mean. So let's say that this is the x component of the vector, and this is the y component of the vector. Okay? And when we're looking at vectors, when we're looking at Cartesian vectors specifically, we're always creating the vectors as position vectors. So we take this vector and we create our Cartesian plane here. I'm going to draw my Cartesian plane out. Right, so this is my Cartesian plane, and this is the origin. We always take the tail end of the vector and we place it on the origin. Okay, so this is vector A. Okay, so we're essentially creating a position vector where the tail end is at the origin, right? So it makes it a lot easier. And in this case, every vector here can be written as a sum of its components. So if we can look at its components here, the projection of vector A on the x component is, we're going to denote this as AX, right? This is the projection of vector A on the x component. This is the projection of A on the y component. This is AY. Now, because x and y are 90 degrees apart from each other, this creates a right angle triangle. Let's call this guy theta. Okay, we can compare the components with the actual vector using theta. And we can understand that sine theta, if we use this as reference angle, sine theta is the magnitude AY over A. So AY here is equal to A sine theta. Okay, so you can actually find the magnitude of the components if you know the angle in between the vector from a starting position, right? And specifically, if we make this on a Cartesian, this is one of the reasons why we call it Cartesian vector, but if we put this on a Cartesian plane, right, we can assume that the reference angle, or the reference point or the reference line here, is the positive x-axis, right? So we're looking at angles, we can look at angles as a positive or counterclockwise rotation from the positive x-axis. Anyways, so that's how you find the y component of a particular vector, and the x component of a particular vector here, AX, is basically equal to A times cosine theta, right? Because we can understand that cosine theta is AX over A. And you can notice that I'm just writing the letters without the vector notation. This implies that I'm only looking at the magnitude, which is what we're looking at in this case. So you can use this for any vector, really, right? But we want to make an arbitrary scale. I usually use this to the right as positive x, negative x. So you can kind of coincide with the Cartesian plane. So up is positive y, down is negative y. So that's really the idea. Now we can also understand that if we have AX and AY, we have the x and y components of a vector. We can actually find the magnitude of the vector by using Pythagorean theorem, right? So we can understand that AX squared plus AY squared is equal to A squared.
That's why.
Oh my god. Sorry guys, this is negative y. Just made a mistake there. But anyways, you can use Pythagorean theorem, and you can rewrite this as AX squared plus AY squared is equal to A squared, right? And if you wanted to solve for A, you can just do the square root. So this is actually a really useful way of determining the magnitude of vectors in two-dimensional space, right? And we'll take a look at three-dimensional space afterwards, but it's good to kind of understand this out first, right? Another reason why this stuff is so useful is because we can actually find the angle of the vector from a certain baseline, because we know that if this is a right angle, then we can utilize the primary trig ratios, right? So as long as you have a right angle triangle, you can use the primary trig ratios, and you can understand here that tan of theta is equal to AY over AX. So theta here is the tan inverse of AY over AX. Okay, this is really useful because you can actually figure out the angle by knowing the two components of a particular vector. Okay, so having said that, you can use all of this to identify the components associated with the vector. Now, let's say that this vector, I position vector A onto a Cartesian plane. It's a position vector because it basically starts at the origin, and the origin here is 0 and 0. And let's say that this vector has a point that represents its tip here, right? So let's say this point here is, let's say it's 3 and 5. Okay, so if it's 3 and 5, we can understand that this portion will coincide with its x component, and this portion coincides with its y component, right? So in that sense, we usually represent vectors as in a form of an ordered pair because it tells us exactly where its x and y component is. Another way to have said this is basically vector A can be written as ax and ay, and this is the component form of a vector, right? Or the Cartesian form of a vector, right? So this is really important, and you can use this to figure out the magnitudes of each, right? So this is basically 3 and this is 5, right? So ax here is 3, and you can think about this as positive 3, right? Because positive 3 means that it's going 3 to the right, and ay here is positive 5, which means it's going 5 up, right? Now, the values, the signs, the positive and negatives are associated with the directions, right? So this is basically the component of this vector, and if you wanted to find the magnitude of vector A, right, the magnitude of vector A here, you can also show magnitude using these absolute value brackets, is basically ax squared plus ay squared, which is basically ax squared, which is 3 squared, plus ay squared, which is 5 squared, which is 9 plus 25, which is square root 34. Okay, so the magnitude of vector A here is square root 34. Right? If you want to figure out its location in the Cartesian plane, if you want to find theta, right? If you want to find theta, you just use the tan ratio. Right? Theta here is the tan inverse of ay over ax, which is basically theta is equal to the tan inverse of 5 over 3. And in this case, theta is equal to, if I do the tan inverse of 5 over 3, I'm just going to punch this in my calculator. You get about 59 degrees. Okay, I'm just rounding to the nearest degree. So this is basically 59 degrees. So that's why this stuff is useful. You can break down a vector in a form of its components, right? So I'm going to show you guys how to use this to do some vector addition. So previously you guys have looked at adding vectors, specifically geometric vectors, using either the triangular method or the rectangular method. The triangular method here, if I was adding vector a plus b, we can understand that vector addition is commutative, so it's the same as b plus a. If I was adding vector a plus b, it would just basically be, I start with vector a here, and then I add vector b to that. I add a projection of vector b to that. Right, my resultant here, remember I started here, right? My resultant here is you're going from initial to your final position. So this is your resultant, and this resultant is vector a plus b. It's your resultant vector. Okay, we'll call this r for a resultant vector. So I'm going to use r commonly as a resultant vector. And that works out pretty well if we don't really have values. If you do have values, you can also use sine law, cosine law. However, it's not as systematic. It's very tedious. I'm going to show you guys a much more systematic method of doing it, and this is going to be employing our notion of component vectors, right? That you can break down any vector as a sum of its components. So let's do that, right? So if we are going to do that, I'm just going to erase all of this. But if we are going to do that, let's break down each vector as a sum of its components. So we said earlier that each vector can be broken down as a sum of its components. We're looking at a two-dimensional grid here. So this is a vector in two-dimensional space, R2 space. Right? So it's going to have an x and y component. So in this case, if I'm looking at the x component of A, which is going to be here, this is the projection of A on the x component. So this is ax, right? So remember, just put the vector arrow here. And A will also have a y component up here, and this is the projection of A on the Y component, AY. Okay, we can use the subscripts to show that. And we can call this angle A if you want. I'll call this angle A, right? Or we can call it theta or beta. You know what? Let's use a different angle notion. Whoops, sorry guys. We can call it A. We can call it theta. Let's use theta. It's just more common. Call this theta. Okay. So in this case, if we wanted to look at the magnitudes of these two, we need to understand that we need to first create a system. This is positive y, sorry. This is positive x, this is negative x, and negative y. So in the upward direction we have positive y, in the rightward direction, we have positive x, in the leftward direction we have negative x, and in the downward direction we have negative y, right? So having said this, both of these angles, both of these directions in terms of x and y are positive, right? So if we wanted to write vector A, we can basically write it as the sum of its two vectors. So we can write it as a sum of its two component vectors. So vector A here is its x component plus its y component, right? And we can understand that AX here is basically cosine theta times A, and should be positive, and AY here is positive sine theta times A. Okay, and the reason I'm writing positive is because of the fact that they're in the positive direction. So make sure you put the signs, and the signs are basically really important for the direction. That's really what it is, right? So you have positive A cos theta, positive A sine theta. Now we're going to do the same thing for B, and you can notice that for vector B here, the x component, I'm going to call this vector BX, it's going in the opposite direction. It's going towards negative x. So that's why we have to write a negative here, right? But in the y direction here for B, your components still going in the positive direction. So this is positive BY. Okay? And we can understand here that for vector B, we can write this as, let's do it here, but vector BX here is, and let's call this angle alpha, or let's call it beta. Okay, this is angle beta. Okay, you can use any letter, it doesn't matter. For B, for the x component of vector B, we're going to have negative cosine beta times B. I'm just going to write the B in front. So negative B times cosine beta, right? And this is the magnitude. This is basically vector B, right? So I'm just using B to represent the magnitude of vector B. And if you want to find its y component, By, it's going to be positive B cosine sine beta. Okay, so y tends to be sine, x tends to be cosine, and the idea is this is positive because it's going in the upward direction. Now the reason we looked at each of these components is if I wanted to add vector A plus vector B, if you're adding two vectors, you have to add up the x components and y components collectively, right? So you add the x components together and you add the y components together. Now we can write vector A here as ax, ay. We can write vector B as bx, by. Okay, this is basically the Cartesian form of the vectors, right? And in this case, vector A can be written as a cosine theta, and y in this case is a sine theta. Okay, and vector B can be written as b, negative b cosine theta, and b sine, sorry, not theta, we'll use beta because this is a different angle. Negative b cosine beta and b sine beta. Okay, so if we're figuring out the resultant vector also has its two components, a plus bx. We'll use a different bracket here. A plus bx and a plus by. Okay, so those are its two components, right? And the resultant vector's components on the x, and I think what would be easier is if we actually wrote this as r, then you don't have to think about it as two things. We'll call this guy r. Okay, so collectively this is basically Rx, right? And then this is Ry. This is just another way of looking at it, right? And Rx here is the sum of all the x components. Rx is basically the sum of all the x components, which is basically Ax plus Bx. And the magnitude of Ry, right, is the sum of all the y components, which is Ay plus By. So technically we're adding these two together to find Rx, we're adding these two together to find Rx, and we're adding these two together to find Ry. Okay? So if we do that, if I add all of these two together, you have to employ the same, you have to employ the signs. The signs are really important, right? So that's why technically this should be a vector, right? Because directionality is important. And in this case, if you're adding the x component vectors together, you get a cosine theta minus b sine beta. And if you have, b cosine beta. If you have these values, you can actually figure that out. So I'm just creating a template, but I'll show you guys this with numbers. And for Ry here, you're adding the two y components, right? So if you're adding the two y components, you get a sine theta plus b sine beta. Okay. Once you have Rx and Ry, we can understand that vector R here, it's composed of these two x and y component vectors, and if you want to solve for the resultant, you can just basically use Pythagorean theorem. So you do Rx squared plus Ry squared, right? And once again, these points, because vector R is Rx and Ry, you can use these coordinates to plot or to figure out where your R vector is, right? So R can be located like somewhere here, for instance, right? If R was located, let's use a different color, but if R was located somewhere here, when we did our triangular method, you can use this notion to figure out the magnitude as well as the angle, right? So the angle here would be tan inverse of Ry over Rx. Okay, so that's basically the template for component vector addition. I'm going to show you guys how to do this with numbers. Okay, so let's consider the following information. Determine the resultant vector of vector a plus b if a is given as the point -3, -2, and vector b is 4, -1. So the first thing you want to do is let's break down each vector into the sum of its components, right? And in order to do that, I'm going to make the x-axis the reference. Okay, so this is basically Ax. Now, because we're using our Cartesian plane, this is positive y, positive x, negative x. So this is the negative direction of x, right? So this should be negative Ax here. Okay, so this is negative Ax, and then this here would be positive Bx. Okay, and in this case, we have, because it's going in a negative direction, we have negative Ay, and this is also going in a negative direction, we have negative By. Okay, so it's good to kind of draw this out and figure out some of the directionalities associated with it. And we understand that because we're given the points here, we can actually just utilize those values. So in this case, Ax is equal to, and we know the point, this is -3, -2, so this should be -3. So Ax is -3. Okay, Ay here is, we know this is -2, right? And vector b here is 4, -1, so Bx is positive 4, and By is -1. Good? Okay, now that we have these points, if we want to find the resultant vector, what you want to do here is add the respective components, right? So the resultant vector is vector A plus vector B, and the resultant vector is also can be written as a sum of its components. This is the Cartesian form of that vector. So the resultant vector is Rx, its x component vector plus the vector sum of its y component. Okay, so it's the x projection of the resultant, y projection of the resultant. The x projection of the resultant is the sum of all the x components. Okay, and the sum of all the x components includes vector Ax plus vector Bx. Now we have these values, and because we are looking at the directions, the negative and the positives are important. We have negative 3 plus 4, because we said right is the positive direction, left is therefore the negative direction. So we basically get 1, right? The y component of the resultant vector is the sum of all the y components, which is basically ay plus by, which is negative 2 plus negative 1, which is negative 3. Okay, so now you can see that your x vector is 1, your y value of the resultant vector is negative 3, so your resultant vector has the coordinates 1 and negative 3. This is really important because you can actually pinpoint exactly where your resultant vector is. So I'm going to draw my resultant vector in yellow, and if it's 1 and negative 3, we can imagine that if we had to kind of sketch it here, let's say that it's somewhere here. And you can do this if you have a much better Cartesian plane. You know what? I'm going to go down here. This is 1 and negative 3. So you can actually see this when you actually draw your Cartesian plane. I'm just creating a sketch. But this is your resultant vector, guys. So this is your resultant vector. Okay, and this tells you that your resultant vector, and if you wanted to draw this on a separate Cartesian plane, this tells you that your resultant vector has an x component of positive 1 and a y component of negative 3. Right, and you can actually find the magnitude of this. If you wanted to find the magnitude of this resultant vector, you're basically doing rx squared plus ry squared. Now you know the x and the y components of the magnitude of each, so you get 1 squared plus negative 3 squared, which is 1 plus 9, which is square root of 10. So the value or the magnitude of the resultant vector is 10 units. Okay, so this is just the magnitude, so I'm not going to add the vector arrow. This is just the magnitude. If you want to find the direction, we want to find the angle between this. And to find the angle between this, we know that x and y are 90 degrees apart. So theta here is the tan inverse of 1 over negative 3. Theta here is basically, if you punch this in your calculator, I want to keep this in degrees. You could convert it to radians as well. You're just looking at the absolute value of this, but it's going to be negative 18.43, but we're just looking at the magnitude of the value, so it's 18.43 degrees, right? And you can say that this is, if you're starting, if this is your reference, if positive x is your 0 degree mark, right? You're basically going all the way here. So you can do, theta can be equal to positive 18.43 plus 270. It's 288.43 degrees. So you can say it's a positive rotation of 288.43 degrees counterclockwise from the positive x-axis. That's the idea. That's basically how you can use component addition. Okay, so let's consider the same question, but this time I'm going to find the resultant vector, vector A minus vector B, right? So if you're looking at vector A minus vector B, you can think about this as vector A plus negative vector B. So negative vector B means you're finding the opposite vector of negative B, right? So the opposite vector of negative B, of vector B here, sorry, not negative B, but vector B should kind of look like this, right? So it should be, whoops, got that better, but it should be, there's like a little error here, but it should kind of look like that, right? And it should have the coordinates negative 4 and positive 1. You can see how the components, right? If vector B is written as 4 and negative 1, right? And this is basically its x component vector, which is 4, its y component vector, which is negative 1. Negative B should be the negative values of these components, right? So you basically multiply, you do scalar multiplication of this vector, and you get negative 4 and positive 1, right? So negative vector B here should have these coordinates, where the x component of vector B is negative 4, and the y component of vector B is positive 1. Now we can use the same notion here and figure out the resultant vector, right? Because we're also given vector A here. So vector A was given as negative 3 and negative 2, and we stated that if you're finding the resultant vector, and this time the resultant vector is vector A minus vector B, which is basically vector A plus negative vector B, right? You just have to add all the x components together and the y components together, right? So think about the resultant once again as Rx and Ry, right? So if we want to find our x component of a resultant vector, we're going to add vector Ax plus negative vector plus, vector Bx. Now in this case our new Bx vector is negative 4 and Ax here is, if we look at this, Ax is negative 3, so this is negative 3 plus negative 4, which is negative 7. Sum of the new y coordinates, right, are now Ay plus By. Ay here is basically negative 2, plus By here is plus 1, this is negative 1. So our resultant vector's new coordinates are negative 7 and negative 1. If we wanted to look at its location now, our location here, sorry guys, sorry about that. Our location here is now negative 7 and negative 1, so it's going to be like, this would be negative 7 and negative 1, so it should be here. This is our new resultant vector. So this is negative 1, this is negative 7, right? And this should be a resultant, and in this case you want to solve for the magnitude, right? So the magnitude of the resultant here is the square root of negative 7 squared plus negative 1 squared, which is 49 plus 1, square root of 50. Okay, so it's going to give us square root of 50, which is the magnitude, right? And if you want to find the angle in between, if you want to find this angle, theta, right? Theta is equal to the tan inverse of negative 1 over negative 7. Cancels out. So theta, if you plug this in to your calculator, it's going to give us 1 divided by 7, approximately 8.13 degrees. Right? And if you wanted to write this, so if this is 8.13 degrees, if you wanted to write this in terms of the positive x-axis here, right? You're doing a full rotation. It's going to constitute 180 plus the 8.13. So 180 plus 8.13, it's about 188. So theta is equal to 188 degrees. So let's say that this was beta instead, right? So beta is a related acute angle, right? So this is our angle associated with it, right? So the magnitude of vector r is square root 50 units, and it's basically 188 degrees counterclockwise from positive x. Okay, guys? Okay, let's take a look at an application question. A plane is steering at south 83 degrees east at an airspeed of 550 kilometers an hour. The wind is from north 70 degrees east at 85 kilometers an hour. The ground velocity of the plane, you want to find the ground velocity of the plane to one decimal. Okay, so first, before we kind of tackle this question, let's first define what ground velocity is. And ground velocity is the resultant velocity. And when we're looking at motion of a plane, we need to look at this relative to something else. Well, we have an airspeed of 550 kilometers an hour. This is basically the velocity of the plane relative to the air. Okay, so let's do you know what? Let's do wind, okay, or air. Doesn't matter. So let's do velocity of plane relative to air, and this is basically, I'm gonna let v subscript pa, v sub pa, represent the velocity or the airspeed of the plane, and the airspeed of the plane is basically in kilometers an hour. Okay, or you can think about this as the velocity of the plane relative to the air. Okay, I'm going to also let the wind speed, which is basically the airspeed relative to the ground or relative to the earth, AE, as basically the wind speed. Okay, and you guys would have, if you've taken any physics courses, you would have understood. You can understand this in a higher level of detail to understand relative motion, but for the time being, I'm just going to summarize just a general way of doing this question. So we have the airspeed, which is the speed of the plane or the velocity of the plane relative to the air. We have the wind speed, which is the velocity of the air relative to the earth or the ground. The earth and the ground are used simultaneously. It's the same thing, interchangeably, right? And what you want to figure out is the velocity of the plane relative to the earth, right, which is the ground speed. So let a v sub pe represent the ground velocity, because velocity is basically a vector, right? So it's going to have a magnitude, which is speed, and a direction. So the ground velocity in kilometers an hour, and basically the ground velocity is a vector sum of the airspeed, right, and the wind speed. Okay, so the ground velocity v sub pe, the velocity of the plane relative to the earth or the ground, is equal to the velocity of the plane relative to the airspeed, plus the velocity of the air relative to the earth, the wind speed. Okay, so that's our vector sum. So we need to figure out what the vector sum is going to be. So in order to do that, I'm going to be utilizing component addition. I'm going to be using my quadrant bearing system. Okay, so I'm going to first draw out my quadrants here. Okay, so this is north, this is east, this is south, this is west. Right, I'm going to use this interchangeably with positive y, positive x, and negative y. Okay, and what I'm going to do here is my airspeed is 550 kilometers an hour, and it's going south 83 degrees east. So starting in south and going 83 degrees east, I'm going this way. So this is my velocity of my plane relative to the air. Okay, so and this value here is 550 kilometers an hour. Okay, we can understand that this angle here is going to be 7 degrees because this angle here is 83 degrees. Okay, now what we need to do next here is we need to also look at the wind, and the wind is coming from, and this is a really important term, it's coming from north 70 degrees east. Well, first let's figure out what north 70 degrees east looks like. So we're starting at north, we're going 70 degrees east. Let's say it's like somewhere here. Okay, so this is north 70 degrees east, but because the vector is coming from north 70 degrees east, it's basically going south 70 degrees west. Okay, I'm going to shorten the vector down a little bit. So the wind here is actually going south 70 degrees west. Okay, and in this case, we can understand that this angle here should be 30 degrees, and this is the velocity of the air relative to the earth, or the wind speed, and this is 85 kilometers an hour. Okay, so the next thing we want to do here, we're going to find the ground velocity. What I'm going to do here is I'm going to break down the vectors into a sum of its components, right? So to find my x component, I'm going to start with my plane, or the airspeed. So this is the velocity of the plane relative to its x component, so we'll call it v sub pax. Okay, and this is the velocity of the plane relative to its y component. Okay, we'll call this v sub pay, right? And we can use the angle in between that, right? And I want to rewrite each vector here in a component form of its two x and y components. We are looking at a question in 2 dimensions, so I'm going to look at its x component and its y component. Okay, so I want to rewrite it like that. So to do this, we can understand that the x component here, if we create an arbitrary scale where we say that east is positive x, then west should be negative x. And conversely for y, if we say north here is positive y, then south should be negative y. So that's the arbitrary scale that we've created. And in this case, we have cosine 77 degrees times velocity of the plane, which is 550. Okay, so I'm going to punch this out. Make sure you keep your calculator in degrees, because we're basically given values in degrees. Cosine 7 times 550. So this is going to give me 545.9 kilometers an hour. Okay, and I'm going to also figure out the y component of the airspeed vector. So the y component I'm going to be using sine, we can notice that the y component vector is going down, right? So there's going to be a negative sign in front of it to denote that we are going south. So the y component of this vector is going south. So we have negative sine 7 degrees times 550, right, kilometers an hour, which is going to give us, if I just punch this out, this is going to give us negative 67.03 kilometers an hour. Okay, so our velocity of the plane relative to the air, or the airspeed of the plane here, is 545.9 kilometers an hour and negative 67.03. Okay, so we figured out the plane. I'm going to do the same thing for the wind, right? So for the velocity of the air relative to the Earth, so to find the velocity of the air relative to the Earth, I'm just going to use the 30-degree angle, and you want to tend to use the angle that is using the x-axis as a reference, right? So in this case, our x component looks like that. Okay, so this is the velocity of the air relative to the Earth on its x component, and this is the velocity of the air relative to y on its y component, right? Kind of overshot that a little bit, but once again, it's a sketch. So this is on the y component, right? And you know what, we'll just put the, whoops, get rid of that, we'll put that here, so it'll just look better, right? And in this case, if you want to look at the vector, velocity of the air relative to the Earth, or the wind speed, the velocity of the air relative to the Earth here can be written as its x component and its y component, so V sub AEX and V sub AEY, right? So V sub AEX, you can notice that the x component of this vector is going west, right? So it should be negative. So this should be negative cosine 30 degrees times its initial vector 85. So if we plug this in to our calculators, get negative cosine 30 times 85, which gives us negative 73.612, and V sub AEY is equal to, you can notice that the y component is also going south, so this should also be negative because of our scale, sine 30 degrees times 85. So in that case, we should get negative 42.5. And collectively, our vector here is negative 73.612 and negative 42.5. Okay, so now that you have the two vectors, right? So we have these two vectors here. You want to find the vector, the sum, right? So you have the airspeed here. This is the velocity of the plane relative to the air. You have the velocity of the air relative to the Earth, or the wind speed. And if you want to find the ground velocity, you add these two together. So the ground velocity here, I'm just going to do this in yellow, velocity of the plane relative to the Earth is basically equal to 545.9 minus 73.612 and negative 67.03 minus 42.5. So if I crunch this out together, I get 545.9 minus 73.612. That's going to give me 472.288. Okay, I can round it off at the end. And this guy here is negative 67.03 minus 42.5. So that's negative 109.53. Just to keep it consistent, I'm just going to round this value. So 0.288, I'm just going to round it to 0.29, right? So this is what the velocity of the plane relative to the Earth looks like. This is the vector. So what this really means is this will tell us the location of the resultant vector very accurately, right? So if I plot this on a graph, then I can notice here that the x component of my resultant velocity, or my ground velocity, is going to be in the positive quadrant, right? So if we're looking back on our Cartesian plane, which is also equivalent to the Cartesian rows, north, east, south, west, right? And this is positive y, this is positive x, this is negative x, this is negative y. we can notice that this first portion here just represents 472.29 east, right? And then this portion here is basically 109.53 south, right? So if it's negative y, it's south. If it's positive x, it's east. Okay, so we're just going to use that to plot this on our grid here. And if we do that to plot this on our grid, I'm going to go this value east. So this is my x component of my ground velocity, right? V sub PEX. And I'm going to go, and once again, I'm just sketching it. I'm going to go this much south. Okay, so this is my y component, so V sub PEY, right? And in this case, the x component here was 472.29, right? And the y component here was 109.53, and my resultant should be here. So it tells you exactly where your ground velocity is. You can also figure out your angle theta. Now, we want to figure out what the magnitude of the ground velocity is. So the magnitude of the ground velocity is going to be, we're just going to use Pythagorean theorem, so 472.29 squared plus 109.53 squared. And you can just put the negative here, but because you're squaring it, right, it should cancel out, right? So you're going to square, you're going to use Pythagorean theorem, and if you solve for this, if I punch this in my calculator, right, I get 472.29 squared plus 109.29 squared. If I square root this, I get 484.77 kilometers an hour. So this is my ground velocity, but once again, it's a velocity, so I also have to figure out my angle. Now, well, because this is one of the benefits of using the component method, you already can see the given angle here. You have your x and y components. You can just use the tan ratio, right? So I'm just going to do this out here. So theta here is equal to the tan inverse of, I'm just going to use opposite over hypotenuse, right? So 109.53. It should be a negative, but we're just looking at the positive value of the angle, right? The negative value of the angle just tells us which quadrant you would expect to find it in. Because it's in the fourth quadrant, if you recall back to cast rule, the angle should be negative, right? But we don't really care about that. We're just looking at the magnitude of the angle. So this is negative 109.53 divided by 472.29. I'm going to do the tan inverse. So let's figure out what theta here is. So yeah, the question is a little long, but I think as you get these concepts down, you can figure out the answer very accurately. So this is 13.056. They want us to look at values into one decimal place, and I'm assuming that it also refers to angles as well. So we have our value here, and because you can notice that this is in the fourth quadrant, you can write this as east 13.1 degrees south. Okay, so that's what this kind of refers to. So collectively, our answer here, I'm just going to kind of make some space here. Okay, so collectively, our answer is, therefore, the ground velocity of the plane is approximately, it's really important to just kind of include the units as well, is approximately 484.8 kilometers an hour in the direction of east 13.1 degrees south. Instead of writing 13.1 degrees south, you can also utilize this value here, right? So you can also use 90 minus 13.1 degrees south, which is basically 76.9 degrees, right? Or you can say south 76.9 degrees east. Okay, so you can use either of these directions, but that's your ground velocity of this.